obviously I'm not going to do everything that you need to know and practice knowing about electronic structure of transition block sets. So what am I trying to do? What I'm trying to do is to provide you with a categorizing or broad stroke understanding, providing you with a language of thinking about the electronic structure of transition metal compounds. So that you in your mind will be able to think of transition metal oxides, each of them as not an independent entity, but in relation to each other. Try to appreciate why this fantastic variety of properties that these compounds show, how they're interrelated, that they're not completely independent. You don't have to understand each of them separately. There is some underlying theme that connects all of them. So I'm trying to bring out that underlying theme, the connectivity, and providing you the language that you need to think about it. Okay? That's my main attempt. Rather than trying to tell you very specific thing about a specific transition metal compound. So I'll remain very broad stroke and necessarily a little superficial at times, but hopefully I'll give you enough indications which way you need to move if you want to understand one specific transition metal compound at great depth in all its complexity. Right? That's the basic idea. So what I normally try to cover, of course, I'll be covering electronic structure. And electronic structure, in some sense, controls all properties. All properties that you know of, and I'll come back to that later. But one of the properties that's very important is magnetic structure, but I don't think I'll have time to get in depth about magnetic properties separately. That normally constitutes a part of the lecture course that I give, but that 4 hours lecture is too short for that. So I'll only be alluding to magnetic properties in passing, once in a while, but not tackle them at great depth. Maybe that will be some other time. And then I'll also provide you some tools, experimental tools, after having understood how to think about them. What are the kind of experimental tools that you have to understand electronic structure, and so far earlier understand magnetic structure as well. And then a few case studies, some schematic, some real, trying to illustrate how we apply what you have learned from the first 3 categories in specific cases. So let's get started. A few terminologies and basic concepts, and some of which has already been covered. For example, this has been talked about a lot, that the electron's properties or motion, we understand in terms of the fundamental equation, which you can write as H psi equal to D psi, which could be the Schrodinger equation that has been talked about at length in the morning. So now this H, the Hamiltonian operator, contains 2 parts, you know that. One is the kinetic energy part, that's T, the operator, and the potential energy part is V. Essentially, you know that a quantum problem is completely defined once you define the potential energy. So defining a quantum problem essentially boils down to defining the potential energy. So let's take the simplest potential energy, the simplest problem, where V is identically equal to 0 everywhere. That's the first quantum mechanical problem that we are talking about. So that's the motion of a free electron. If there is no potential, which is equivalent to saying if there's a constant potential, because that you can always set to 0, don't worry about it. So that's a free electron, which says that P psi equal to E psi essentially, because the V part goes to 0. You know the solution of that, all of you, because that's the first thing you've done. The energy of that, it's a free electron wave function, and so depending on whether it's going in the x direction, y direction, it will be ikx, ay type of dependencies. And the energy as a function of k, the momentum vector, is h bar squared k squared over 2. That's the standard energy, total energy of the free electron. If I plot this energy as a function of k, that looks like a parabola because of the k squared dependence, because h bar squared over 2 is a constant. And this is what we call dispersion. So dispersion, every time I talk about dispersion, that is referring to how energy changes with momentum. Okay. And another thing that I'll be talking about, which is called the density of states, which is defined by this quantity, it essentially counts how many allowed electron states are there in a short interval of energy. And that in the limit of that short interval, I take the interval going to 0. So basically, it's a statement about the density of number of electron states at any energy, which in this particular case that you have written down is exactly solvable, and that has this dependence, which is the density goes as you can see, e to the power half. Okay. So this is the density of states. So most of the time, we'll be referring to this energy dispersion relationship, E versus K, which for a free electron turns out to be h bar squared K squared over 2m, but in other systems it will be different, and density of states of this kind. Of course, yes. Pardon? Yes, absolutely. I mean, in this particular case that I'm talking about, exactly this one, that this three-dimensional system. So, yeah, that's no, absolutely. Since I mean, that slide flashed in my mind that how 0D, 1D, and 2D would be very different. But, okay. And also remember, this relationship is possible only if the energy I've written on as a function of momentum, which means I've made an assumption there. Assumption which is true in this particular case is that momentum is a good eigenstate. It's a every state of the free electron has a well-defined momentum. So momentum operator has simultaneous eigenstates with the energy. That's the time when, so if you are talking about, like, for example, an atom or a molecule, this will not be the case, but since I'll be talking about solids, a periodic solid where again this assumption is valid, so I'll not make that fine distinction and point out that I'll be talking about energy dispersion, where energy will be a function of the momentum vector, and there will be some density of states. In this particular case, it will be power half-like, and in other cases, it will be in general more complex. These are two fundamental points. Now, let's get a bit more complicated, and this is the point that already Sushanta has introduced in the morning, the tight binding model. These will be the few equations that I will show you. If you don't understand them, don't worry, I'll just illustrate the basic point. Because what we are trying to describe, as I just now said, is an infinite solid, where periodicity is valid. So there's an infinite periodic lattice, which I'm trying to understand. And that is very often, very well, I mean, a starting model to describe the electronic structure of that is the tight binding model that Sushanta introduced with two sites. But what I'm now talking about is where you have infinite such sites, and think of a one-dimensional chain of atoms at distance a from each other, periodically arranged. Such that in general it could be that's a lattice, and each lattice can have several basis atoms. It can have one atom per lattice site, it can have two atoms per lattice site, it can have 5 atoms per lattice site. In general, it has NB atoms per lattice site, so we call them the basis atoms. And the number of basis atoms we define as NB, whose positions, these lattice sites are defined by this quantity, and this is the one that then tells me where that particular atom is with respect to the lattice point. And the atomic orbitals that sort of had introduced in the morning are some objects and functions which are centered at that distance r plus dj. You can see r minus r is the variable in space, and this is the position where that particular atom is, so that it says that this function is sitting at that particular atom site. It's a function defined with respect to the atomic point wherever that particular atom is sitting. We can, since this is a periodic problem, I know that the basis functions have to be block functions. One can generate block functions. This is a point I'm going to gloss over now because I don't want you to get bogged down into these equations. These equations are very standard. You'll find them in any book, right? And if you want, I'll provide you with these slides, so don't be in a hurry to write them down either, all right? Because anything that you find in the book, I'm going to skip through a bit faster. And these are, of course, these block functions by construction retain the lattice, their eigenfunction of the lattice transmission. So the periodicity is built into the way I'm trying to solve the problem. And then with respect to these block functions, I can find out the Hamiltonian matrix element which is given over here, okay? Which essentially translates as what I want you to look at is that after the jugglery, mathematical jugglery, this Hamiltonian matrix element becomes the function of the momentum. Okay? And this is the kind of expression that you have to
You
find.
can say that you did a basis change and went from real space to momentum space. So Hamiltonian
It's a little more than that. It's actually my basis functions were both momentum and space dependent. Naturally, that's the block construction. And then the matrix element with respect to that is, of course, because you integrate out the space, you are left with only the momentum. Okay. And then there's also an overlap matrix element that is essentially trying to measure how the block functions that I have created, which are situated on one atomic site, repeated between different atomic sites have different block functions, how they overlap with each other, essentially. That is measured directly. You can see that this is one of the block functions, there is another block function, J alpha and J prime alpha prime denote two different block functions. And when you take the overlap, there's a overlap matrix element, which again turns out to be just because of a delta function in the definition of that, it turns out to be just a momentum function. What I really want you to notice is basically then the problem that H psi equal to E psi that you are trying to solve reduces to figuring out the eigenvalues of this particular Hamiltonian matrix, H of k, in presence of an overlap matrix that's given over here. This, if you notice, okay, so these are the two things that I have defined for you here and here. And what is important for us is this is the band dispersion that I am trying to get by solving this problem. And similarly, the density of states that I'll get once I've got the band dispersions out by constructing equivalent quantity that I have shown you in the first slide. So this is essentially trying to get, if I know the energy of the electron and if I know the electron density, I know most of the things I want to know about the electron. The electronic structure in the first assumption are going to be given by these two quantities. So one is the band dispersion I'm after, and the other is the density of states. But now let me get back. This is just the introductory part. If you have not got the mathematics of it, it is not important. Let me again restate that. What you need to know is that what we are trying to get is how the electron energy is in the system as a function of momentum, because I have a periodic system. If I have an aperiodic system, then it doesn't matter. I'm interested in all the energy states and the density of states.
So just
Yes,
to
sure.
for students to connect what you said to what I was doing, I had a much simpler idea where you only connect to neighboring states. That is, when Sarma will calculate the matrix elements, you will ignore the nearest neighbor couplings, but that is not here.
Not. Basically, type binding model can be, what he's saying is very important. Let me elaborate a bit. So here taking two sides, and in fact, I'll be connecting to the last equation that he wrote down, if you remember, when he had this projection operator, plus, minus, and minus plus, the Hermitian conjugate of it, which essentially take a plus state and convert it into a minus state, and the minus state converts into a plus state. And he had written down the Hamiltonian, do you remember? There was an energy term which was plus projection operator, another energy term that was minus minus, and two other terms which are Hermitian conjugate of each other, plus minus minus plus. So that he was talking about how a state, if you center at one side, how it can hop to the other side. But now imagine you have many such sites. So you can talk about a hopping to the nearest site. You can talk about a direct hopping to the next nearest site. You can talk about a hopping to the next nearest site, etc. That defines a model that you're working with. Most of the time, tight binding model, as the name suggests, works with the smallest hopping range, which is the nearest neighbor. I'll show you later that at times you're forced to go beyond the nearest neighbor in order to provide a proper description of the electronic structure. So the range of hopping is determined by the question that you're trying to ask and the phenomena that you're trying to understand. But the basic elements of those Hamiltonian will be exactly like the one that Sushanta wrote down in the morning. Okay, and I'll show you when I come to that and make a direct comparison between the Hamiltonian that I show and the one that you talked about.
So sorry, another comment.
Sure.
Because of science and advanced materials, you see, today materials have all defects, right? I mean, you can't find materials without defects. When you have deep pairs, then what happens is that you have strongly localized states also. Like these epsilons are deep well sometimes. So indeed, in many applications with deep pairs, the non-nearest neighbor hopping becomes increasingly weaker, and therefore the nearest neighbor hopping actually becomes a good model for highly defected states. But Professor Sarma will also show you where that may break down.
Also. And
actually, experimentally to get to all those things separately is a very complicated problem.
yes, and we'll try to understand how we go about trying to do that. So let me come back to the experimental aspect. And now it's going to go very pictorially, so you can relax. I'm afraid if I put you off with those strange looking objects in the first few slides, you really don't have to worry too much about it.
Sorry, and also the other point is that, you see, I was simply writing a pseudo state of a plus spin or a minus spin, the pseudos, without discussing their detailed positional structure. What you see here is all those details coming in. And in fact, they're also, they're in the back of your mind. They have to be there. Especially suppose you say what happens if you put a magnetic field, how the magnetic field change all those states. These are the things that therefore have to be brought in.
Basically, he wrote it down for any two-level object. What I am connecting to, which he also connected to when he drew the two-symbol harmonic oscillator, as if with one state being the particle at this side, one being particle on that side. And then the transfer between them that he gave a strength of J. We'll come back to that. Let's get back to the transition metal oxides that I promised you.
But it is some comment why that tight binding applies so well to transition metal.
Let me say that right away up front. Okay.
Or D band.
Yeah. I'm just trying to see where I would like to bring that in. I'll come back to it a bit later. I will come back to it a bit later, why it works so well. As again, I mean, you can anticipate what the reason would be. If there is a system where tight binding is going to work well, tight binding, what is it trying to say? It says that I have some sort of an approximate description of a particle or electron being at one site and sometimes hopping to another site. Right? If my particle is such that it's going to be very difficult to associate it with any one site, it's so strongly delocalized that it's sampling over all the states, which means that it can hop to any far away range in very quickly, and whether it's here or there, it's impossible to figure out. A tight binding model, as the name suggests, would not be a good starting point. Tight binding model is one where you can start with an approximate description that is tightly bound to in space.
So for a good metal like copper.
So sodium, I would say sodium. Right? Sodium is not a good place to start. Sodium metal is not a good place to do a tight binding model.